Welcome to note set number 33, where we'll get into the real workhorse method for IIR design, which is called the bilinear transform. So we've looked at a few methods already, two in particular, to be precise, and saw that even though they come from very obvious attempts or methods or ideas, concepts, they lead to less than desirable characteristics for the design. And that's usually the case in engineering. The first ideas give solutions, but not necessarily the best solutions, and it takes time for people to think about it and develop the more complicated but better approaches. So, like I said, here we'll be talking about this thing called the bilinear transform, and technically, transform is a bad name there. It's not like a Fourier transform or a Laplace transform. It's really more like a mapping. It's a mapping from the S-plane to the Z-plane. But nonetheless, bilinear transform is the name that has stuck to it, and this is covered in section 10.3.3 of Proacus and Montelakis, and they give a way of motivating it. I'm going to give a slightly different way, well, a very different way actually, and but we end up at the same place. Okay, so here's our motivation, and as I state, this is different than the Proacus and Montelakis textbook. So the idea is we've got some continuous time filter, and we'd like to transform that, map it into a new filter that's a discrete time filter. So suppose we have the continuous time filter here described by its transfer function, and suppose we had what we thought was an equivalent discrete time system. Now, to compare these, we have to involve sampling and unsampling on the discrete time to compare them in the continuous time framework. I'm choosing to compare them on the in the discrete time side, and to do that we only need A to D converters, and that's because A to D converters are, to describe the ideal situation, is very, very simple to describe. So suppose we take our continuous time system, and we've learned in signals and systems that a fundamental signal to think about as an input signal is the exponential, and in this case it's e to the st, where s is the complex number, any complex number on the s-plane. So for right now, imagine thinking about s as being fixed here. This is a little delicate and subtle here. Think about s as being fixed there. Here we're thinking about s as being the general variable s, and then over here it's fixed at whatever the value is that goes in. So we could put like an s sub 0 on this, and we would say e to the s sub 0 t goes in to a transfer function h of s, and it comes out e to the s0t times h of s0. So the transfer function would be evaluated at the point s is equal to s0. But it's a little easier to just leave it like this, notational wise anyway. And then we sample this thing, which is now just a function of t, so s is fixed at a single value, the value that we put in at the front end. And so we take this function of t and we run it through an A to D converter, and so now the t variable gets replaced by indexed by little n with spacing of capital T, where t is the spacing interval or the sampling interval of our A to D converter. Now, on the other side, suppose we have a discrete time system that we claim is equivalent to this continuous time system. Then if we were to take the same input and sample it, we now get e to the Sn capital T, which we can write as e to the St quantity raised to the n power. and we think of that as a z to the n. Remember, z is a complex number, so e to the st is going to be some value of z. So for a fixed s value, we'll get a fixed z value raised to the n. And when we send that through our system, our discrete time system, we have a result that says z to the n in comes out as h of z times z to the n. So we have exactly that scenario. So we're really going to take, this should be a z there. I'll try to fix that before I post the notes. So that superscript should be a z. So what we get is the transfer function evaluated at e to the st times e to the stn, and we see that if we want these two systems to be equivalent, they should these outputs should be equal to each other, and therefore we can get to this position where we say that in order for them to be equivalent for any s value chosen for our input, then we should be able to set, if we evaluate our discrete time system at z equal e to the st, that it should be equal to the continuous time transfer function. And so we can see from here that this implies replacing z by e to the st. So that gives an implied map from s to z. So as I plug in different values of s here, they get mapped into different z values. Now this mapping has two desirable properties. So one is that the j omega axis, so when we let s be equal to j omega, that j omega axis maps to the edge of the unit circle, so that makes sense. Those are the two analogous parts of the two corresponding planes, and also the left half plane of the s-plane maps to the inside of the unit circle. So the second one tells us that if we start with a stable continuous time system, apply this mapping, we will get a stable discrete time system, and that's a nice property to have. Unfortunately, it has two undesirable properties. So if we undo that e to the st to isolate s and write s in terms of z, we get natural 1 over t times natural log of z. Now you have to extend the concept of natural log a little bit to allow complex numbers inside, and it is possible to do that with a little bit of fuss, but we're going to just wave our hands over that and say, well, whatever that thing ends up looking like, it's certainly not going to, plugged in for every s, give us a rational function of z. We're going to have natural logs of z raised to various powers, and it's going to look ugly. And what we want is an h of z that is implementable, and so we want it to be a rational function of z. The other problem with this is that even though it does map the j omega axis to the unit circle, the way that it maps it is it wraps it. The picture that I have down here, we can understand by looking at this equation here. What we're saying is if we're replacing z by e to the st, now let s be equal to e to the j omega, the z values that we get are e to the j capital omega t, and since that's an angle, we have to view it as a mod 2 pi kind of thing. So our discrete time frequency, which is the angle around the of a point on the unit circle, corresponds to the continuous time frequency times t, which is going to be the sampling interval that we're talking about, interpreted mod 2 pi. So to look at this graphically, if we come over here to this picture, we see that we've got our j omega axis here, and we've got 0 here in the middle, and we've got positive values up and negative values down. And so I've labeled the values here for some corresponding capital T. If this point here is pi over t, when I multiply that omega value. So if I take omega equal to pi over t, multiply it by t, I'm going to get pi, and so that just maps to pi. Okay, so that point maps, well, 0 maps to 0, obviously. Pi over t maps to pi. Minus pi over t maps to negative pi. But now when we go out to 2 pi over t, that's actually going to map back here. I didn't put those arrows on because I figured it would get a little too crowded on there. Minus pi over t maps to there. 3 pi over t maps to there. Minus 3 pi over t maps to there, and so on and so on. And so this becomes a wrapping. So one way we can think about this, let me get rid of all this stuff here in one fell swoop, hopefully. The way that we can think about this is, imagine taking this as a piece of string and putting the 0 part right here and wrapping the string around, and we get to the pi over t, and we keep wrapping and wrapping and wrapping, and likewise we are wrapping in this end as well. So 0 goes to that point, and then this tail starts wrapping like this, wrapping, 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 wrapping. And so that's what I mean by wrapping around the unit circle. And so what that means is that characteristics that are far out on the j omega axis that come from the original continuous time frequency response kind of get mapped back onto, get mapped over and over onto the unit circle. So that's definitely a downside, and it's very similar. In fact, it's almost identical to what we saw in one of the previous methods where we did the impulse invariance approach. So this is effectively the same thing as we've seen in the aliasing approach. And so we need a way to fix this because that severely limits what we can do with this kind of design approach. So here's our steps to fix this thing. So instead of taking z is equal to e to the st, or its equivalent s is equal to 1 over t natural log of z, we're going to look for some other mapping. And what we'd like is, we want the unit, we'd like the j omega axis to still map to the unit circle. So when I say still maps to the unit circle, I mean the j omega axis, but without the wrapping, and also ensures that the resulting h of z is rational. Now, when we start off here, it's not going to be obvious why we're going down this path, but it's one of those things that probably came about from just playing around, the initial researchers probably just played around, and had looked at this problem so many times that they just kind of stumbled upon this. I don't really know how this was motivated. The book does go through a little development from kind of a approximate integration viewpoint, but I'm not convinced that that was the way the initial motivation came. So if we take a look at the hyperbolic tangent, and we take hyperbolic tangent of st over 2, and we expand that, there's a well-known expression for hyperbolic tan that says hyperbolic tan of x is e to the x minus e to the minus x all over e to the x plus e to the minus x. So that's all we've done here, replacing x by st over 2, and kind of ignoring, we're not clearly addressing the issues that, s is complex valued. But this is valid. The next thing we're going to do, take the same function, hyperbolic tangent of st over 2, and expand that in a power series. And so, if you look that up in a calc book, you'll see hyperbolic tan of x is x minus 1/3 x cubed plus 2/15 x to the 5th blah, 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 blah. So we're just doing this with x replaced by st over 2. And again, not worrying too much explicitly about the issue of s being complex. And then what we're going to do is say, well, if we pick t small enough, these st over 2 terms are going to be small over the range, the region of s that we're interested in. And so these terms can be ignored. And so we'll be left with inverse tangent, not inverse tangent, hyperbolic tangent of st over 2 being approximately equal to st. So then we can equate these two things, and that's what we've done down here. And we've taken the t over 2 and swung it over to the other side. So we end up getting something like that. And then we go to this next step here where we factor out an e to the minus st over 2. So if we factor that out of this term, we get a 1. If we factor an e to the minus st over 2 out of this term, we'll end up with an e to the st. And same thing on the bottom. And out in front, we'll have an e to the minus st over 2 over e to the minus st over 2. And those end up canceling each other out. So this is what we have. And then we look at that and we go, aha, well, we had let e to the st be equal to z. So maybe we should here let that be equal to z and see what comes of this. And look what falls out of this. We get that s is equal to 2 over t times z minus 1 over z plus 1. And look at that. This is called bilinear because we've basically got two different linear polynomials of z involved. So that's clear and obvious. The other thing is that we see that we get this part immediately, the rational thing. So if we have a rational function of s and we plug in for every s a rational function of z, you clear everything out, do a bunch of manipulations, you'll always get back a rational function of z. So that's good. So the only thing that we really need to explore is this issue of does it map to the unit circle and does it fix this wrapping problem? So let's take that. So here I'm just pointing out the term bilinear just comes from this two different linear parts. We can rewrite this by factoring out a z inverse from the top and the bottom. We can rewrite it this way. So sometimes you want one, sometimes you want the other. And so our rule for design now will be you give me a continuous time HA of S, and then I replace S by 2 over t z minus 1 over z plus 1. And when I make that substitution, I'll get a rational function of z, which will be the transfer function for my designed discrete time filter. So let's take a look at what this looks like. So just for notation, we know that we can write z in polar form, and we can write s in rectangular form. And so let's substitute that in. So we've got s written. We've got our z's, we plug in our form for our z's, and then we do a bunch of algebraic and trigonometric manipulations here, and we end up getting a real part and an imaginary part. And since the real part, well, s is written as sigma plus j omega, we know that this quantity here is sigma, and this quantity without the j is the omega part. And so now we can check. So if we let r be less than 1, we come up here. Let me try to get rid of some of this stuff here so that we can see this a little bit better. So if we let r be equal to, less than 1, notice that we'll get, it's easiest to see in the numerator, we'll get the something in the numerator that is negative. And if you look at the denominator, you'll see that you'll also get something that's positive there, so we end up getting something negative. So when r is less than 1, we get sigma less than 0. When r is greater than 1, you can go through the same kinds of things. We'll see that we get sigma is greater than 0. And then when we let r equal to 1, notice that the numerator goes to 0, and so sigma is actually equal to 0. And so what that tells us is some important stuff. So when r is, let me do it the other way. So what that means is, even though we didn't prove it this way, we can see that anytime r is less than 1, we had to have sigma less than 0. So that means the left half side of the plane maps to the interior of the unit circle, and so stability is preserved. And when r is equal to 1, we see that we need sigma equal to 0. And so that means that the j omega axis maps to the edge of the unit circle. So both of those are good. So now the last thing we need to check is this wrapping issue. So have we fixed the fact that the j omega axis in our previous mapping wrapped around and around the unit circle, which was not so. So let's look at how a value, how the frequency values in continuous time and frequency values in discrete time are connected to each other. So if we look at this function, just at the omega part, because we're going to set sigma equal to 0, and we'll set r equal to 1 so that we're on the unit circle. When we do that, we look at the omega part here, but we are going to set r equal to 1. And so when we set r equal to 1, we end up getting something that looks like that. And with a trig identity, we can express it that way. And then solving it for omega little omega in terms of big omega, we get this expression. And sometimes we'll use it with the inverse tangent, and sometimes we'll use it to go back the other way with the tangent. But this is telling us how the continuous time frequency, omega, maps to the discrete time frequency, little omega. And we can see that that mapping depends upon the choice of t, which for right now we can think of as a sampling rate. But later we'll see that we don't really need to think about that as the true sampling rate of the used system. We can just think of it as something that we use along the way as a design parameter. And so if we look at a plot of this mapping, we've got omega here, and I've modified this a little bit from the version in the textbook. The textbook plots capital omega t. I plot omega, and so my values along the way are in terms of t. So if I plot this, I'll see this inverse tangent curve, which approaches this positive asymptote and the negative asymptote of pi and negative pi. So what we see here is that no matter how far out the analog or continuous time axis I go, the mapping never goes outside minus pi to pi on the discrete time. So I like to say that instead of wrapping, I'm warping. So it's a kind of not a play on words, so to speak, as much as it is a play on letters. So the bilinear transform doesn't wrap, it warps the frequencies. And this is a fundamental and important idea to understand to be able to properly apply the bilinear transform. So we need that a little bit more. So here's a plot that shows the effect of this warping on the frequency response. So I've just redrawn, I did that again, hadn't done it in a while. I've redrawn the figure up here that we just saw, and I've got the function up here that shows how capital omega gets mapped to little omega. And so what we see is that down here it's linear, and things kind of get mapped pretty much straight away. So if this is our curve for our continuous time frequency response, we can see that the different frequency points get mapped at the low frequencies pretty much almost same to same. But what we are seeing is that as we go further up in frequency, this curve bends over, so there is a reduction in the value of omega as we go up, and it can be quite quite a steep slope. And so what that does is it takes this entire thing that goes all the way out to infinity, and it squishes it down into this region. And in fact, we see these lines, these dashed lines, getting more and more horizontal as we go up farther in frequency. And this last one, even though it doesn't really say it, but this last one is kind of illustrating the idea that capital omega at infinity gets mapped to little omega at pi. So a transfer function in the continuous domain that has a pole or a zero out at infinity, that pole or zero will get mapped to an angle of pi, which really means it gets mapped to z equal to -1. So one thing that we can see here is that our original shape of our frequency response was kind of spread out and maybe goes down slowly. When this thing gets scrunched in, the shape changes some. Now, how much of that gets, how much compression we get is set by the value of t here. So a smaller t will end up with less and less of that compression. A larger t will give us more and more compression. And so picking t has to be done cleverly and appropriately so that this all works out. And we'll go through a couple examples here at the end of these notes that will show how this actually works. All right, next here. So in passing, and we'll use this later, I do want to point out that MATLAB has a command for the bilinear transform, and no surprise, it's called bilinear. So you put in a vector with the coefficients of the numerator of your continuous time transfer function. So the numerator is going to be some polynomial in S. So you put them in the order of descending powers of S. And then you get denominator likewise, and you put in an Fs. Now, just be careful. That doesn't necessarily mean the Fs at which you'll be operating the actual final design, and we'll talk about that as we go through. So it's better to think about that Fs as being 1 over capital T, where for now, capital T should really be thought of as a design mapping parameter for the mapping between continuous time and discrete time. And we'll go through some examples that hopefully will make that concept clear. And so to muddy the waters even more, I'll try to outline these two different approaches of choosing T, and I guarantee you'll hear me say this, you'll read it, and you'll go, huh? But once I go through the examples, come back and read it again and see if you can understand what I really meant. But it's really simpler than what it sounds like here. But basically, we've got two different ways of picking T. The first one is to just pick it for convenience in the filter design. And what that's going to do is force us to think about the design in terms of the discrete time domain. So we'll need to specify our desired frequency cutoffs in the discrete time and then map them back to some appropriate continuous time filter, which will then get mapped with the bilinear transform. So that's one approach. The second approach is, well, we know that we're going to be running a signal through this filter, and it's probably a signal that came from having sampled some continuous time signal. So pick the sampling rate Fs. that's appropriate for the signal that you're trying to operate with. And so then t would just be 1 over that sampling rate. And then once we've done that, if we're going to design our filter from that perspective, we know where our signal spectrum ends up living on the discrete time axis, and then we'll have to find an appropriate analog filter that will map to where we want it to be. Okay, right now is about when you go, huh? It'll hopefully be clearer when we go through the example. So let's go through an example. We'll go through 2 examples. The first one with method number 1, and this is based on the example in 10.3.4. By the way, the textbook doesn't really outline these 2 different methods. They kind of do, but not all that explicitly. So keep these comments in mind, but I'm not going to worry about them too much. So I'm going to illustrate this with an example of a signal, a guitar signal that we looked at in some earlier set of notes. And so we've taken a DFT of our guitar signal, and so we've got a kind of good idea of what the spectrum looks like and what ranges we might need to look at. We also know that we should be sampling the signal, on the order of 40 kilosamples per second or something like that. Technically, you'd probably stick with the CD standard, which is 44.1 kilosamples per second. But I made it easier here, so I imagined that Fs was 40 kilohertz, and so Fs over 2 is 20 kilohertz, which is what we're seeing here. And so suppose that given this signal, our job is to design some sort of resonant peak filter. So we looked at that example in one of our earlier set of notes when we were learning about MATLAB processing. So here's our 5 kilohertz. We can look at pi over 4 will correspond to Fs over 8. So here is the idea of determining our frequency cutoffs in the digital domain. So I would really say I want to peak here at 5 kilohertz. Where does that live with this sampling rate, which I've picked for my signal? Now remember, I've not committed to T for my filter design yet, so it's important to keep in mind that this Fs is not going to be related to this capital T for my filter design. I know it sounds crazy, but that's how we're going to do it. So we're going to take our desired 5 kilohertz and our actual sampling rate, 20 kilohertz, and map it to pi over 4 is where we want the resonant peak in the discrete time world. Okay, after we've designed this discrete time filter. So we need to pick some sort of continuous time filter with a resonance, and this is a good candidate. And I just picked one that was simple. I didn't care about whether the resonance was at 5 kilohertz or not for this actual continuous time filter. I just let it be wherever it was. I said, this is a structure, it gives me the resonance, maybe this will be what I want. And so I just do a little bit of manipulation. So this structure is something that we know, I know anyway, and other signal processing people know. Okay, that'll give me a resonant peak. If I expand out the denominator, I get that. If I factor out the denominator, I can now see, oh yes, I get a resonant peak at 4, an omega equal to 4 radians per second, and with the real part being so small, fairly small, my poles are fairly close to the unit circle, and so that's going to give me a resonant peak. And to just test that out, I plot the frequency response on one side, so I create from 0 out to 16 radians per second. I run my freq s with the coefficients from my transfer function. I plug in my omega values that I computed. I compute H, and then I plot its absolute value, and that's what I have here. And we see that, yes, indeed, we have a resonant peak at 4, which goes up to a height of 5. And I've plotted this all the way out to 16, and we see that it decays down quite a lot by the time we get to 16, which we'll see is good. All right, let me try to get rid of a bunch of this stuff here. And okay. So what we want to do is take this filter and convert it into a discrete time filter that has a peak at the discrete time frequency that our 5 kilohertz is getting mapped to by sampling. So we've got two different mappings going on here. We've got the frequencies of the signal getting mapped into discrete time frequency. And then we have this other stupid little filter whose resonant peak is at 4 radians per second getting mapped by a different mapping into the discrete time frequency axis. And that's why we have to think about Fs being one thing and T for our filter design being an entirely different one. So let's pick the T that we need to put this 4 radians per second at pi over 4. So that's what we want to do here. We want to map capital omega equal to 4 radians per second into pi over 4 radians per sample. And here's the mapping that takes little omega into capital omega. And so if we plug in the pi over 4 here and we plug in the 4 here, we get something that looks like this. And the only thing we don't know is capital T. Solve for capital T and I get 0.2071. And so that's the T that we're going to use. Now, one last thing that we check. We've seen, aliasing of these filters before. Well, we want to just make sure that our sampling frequency is kind of far enough out above where the important part of our filter is, even though there isn't really any sampling rate going on or sampling going on. It's just kind of a good idea to just kind of make sure that 1 over t, well actually 2 pi over t, ends up kind of being out here away from where the interesting part of the filter is happening. Okay. So we now continue on here, go to the next slide, and we use our bilinear transform. So here are the two sets of coefficients from the numerator and denominator. We put in our 1 over t here, because remember the bilinear command calls for fs, and it's important to remember we're picking that to be 1 over t from our needs for the filter, not 1 over t or our fs for the needs for the signal. So it's kind of like saying we're mapping two different frequency ranges into the same discrete time world. So you could kind of think about it as taking shrinking something down and expanding something up, and they both end up kind of being consistent with each other. That's sort of like what we're doing here. Anyway, we run the bilinear transform, and it spits out two different 3 coefficient vectors, numerator and denominator. We plug those in. Here the z powers are decreasing as we go from left to right, but they start at z to the 0. So we're looking at the negative power version of this. And if we do that, we take this filter, we can use the z-plane command to find what the pole 0 plot looks like, and no surprise, we see a 0 here and a 0 here. So one kind of tacking things down near zero frequency and tacking things down up near pi. And then we see two poles very, very close to the unit circle that are causing the resonance, and they are exactly located at pi over 4 radians on the angle on the unit circle, and that corresponds to pi over 4 radians per sample. And this is my almost always used normalized scale. And so if you compare this filter to the continuous time version of that, you'll see that we did a good job at transforming this. And in fact, we did get a resonant peak at the frequency that we want. So notice that our filter's 4 radians per second peak got mapped to pi over 4 radians per sample, and our 5,000 hertz signal components also got mapped to the same point. So we kind of mapped the signal components and the frequency components differently, and they kind of end up at the same place. So that's method number 1. And so if we think about method 2, and this is the way that I think most people think about it, and if you look at some of the commands that are structured for MATLAB, we'll see at the end of this example that this is kind of the way that most people, most filter designers think about it. So we're going to pick the T and use it for our filter. Well, let me say it this way. That was poor wording. We're going to pick the T based upon an appropriate sampling rate for our signal, and then use that same T for the filter design. And but that will cause us to have to be a little more particular about the choice of our analog filter. Notice in method number 1, we just picked any old filter that kind of looked right. We didn't care whether it had a resonant peak that had anything to do with 5 kilohertz. That resonant peak could be anywhere, and we ended up mapping it in the discrete time to where we wanted it to be. So here what we're going to do is, once we've settled on an appropriate sampling rate, and we're settling on using the resulting T for both sampling and for our filter design, then we kind of have to make sure that the continuous time filter that we pick is kind of, not exactly as we'll see, but close to having the right characteristics for the actual signal. So it's more like comparing the signal and the filter in the analog domain, and then mapping everything to the discrete domain. Whereas method number 1 is more like taking the signal separately, taking the filter separately, and then mapping them so that they both match our goal in the discrete time world. Everything works out exactly the same way. It's just 2 different ways of thinking about it. So just for a little bit of illustration here, and actually to be honest, to make it a little easier to see the characteristic of the analog filter, we're going to focus on a low-pass filter here rather than this resonant peak. So suppose we've got this signal down here, and we'd like a cutoff at 5 kilohertz, a low-pass filter to cut it off, and we're using an FS of 40,000 samples per second. So as soon as we have that, we say T is equal to 1 over Fs, which gives us 2.5 times 10 to the 5th. So that's going to be the T that we use both in our A to D converter and in our filter design. And excuse me, we then pick a very simple first order low pass filter. Here's our analog prototype, and we don't know what to pick for omega sub c. That's going to be the cutoff frequency. Now you would think that you'd want to make that consistent with the actual frequency that you want to be filtered. So we said we want we want this to be equivalent to filtering the analog signal at a cutoff of 5,000 hertz, which would be 31,415 and change radians per second. But remember the warping. The bilinear transform warps everything down. So if we actually put that number in, then applied the bilinear transform, we would end up with a cutoff frequency that's lower than what we want. So we don't want that. So we kind of have to fudge for that. So here's our signal frequency, 500 hertz, and we can convert that as we did before into discrete time, but we can also just kind of think about converting that 5,000 hertz into, we've got 5,000 times 2 pi, so that converts it into radians per second, and then times t, so t is 1 over 40,000. So in reality, we can think about this quantity here that I'm erasing, and we'll soon circle again. This quantity here is capital omega t for our cutoff. So if we want to map that to the right frequency, we would use this mapping. But what we want to do is reverse that. We want to pre-warp. So we want to move 5,000 hertz out a little bit farther. So we take the inverse of this bilinear warp and map things back out. So we've got capital omega is equal to 2 over t, tangent of omega over 2. So remember, omega is actually this pi over 4 radians per sample, but that's just this quantity here. So we can plug that quantity right in here for the omega. We put a 2 in there, and we now figure out what our analog cutoff frequency should be if we actually evaluate this with our chosen FS of 40,000. We will find out that we get 33,137.08. So we've taken this 5,000. If we just map it according to converting into radians per second, we get 31,000 radians per second. If we pre-warp it, move it out a little bit, instead of 31,000, we get 33,000 radians per second. So the book doesn't call this pre-warping, but there's a lot of books that do call this pre-warping. And it's a very common way of thinking about the bilinear transform. It sounds confusing, but it's not. It's just we know that whatever omega c we put into our bilinear transform is going to end up showing up at an effective frequency lower than where we really want it because of the bilinear transform's warping. So we pre-warp it out a little bit farther first, and then let the bilinear transform warp it right back to where we want it to be. And the equations just tell us, where to warp it to, where to pre-warp it to, so that it gets warped back to exactly where we want it to be. So now we just call our bilinear transform, and in our transfer function, we don't put in 2 pi times 5,000, we put in the pre-warped value of that. So instead of putting in 31,000 something, we put in 33,000. So we put in the 33,000 there, we put in the 33,000 there, we put in our sampling rate, 40,000, we run bilinear, and we get 2 numerator coefficients, 2 denominator coefficients. There is our transfer function. Here's our pole zero diagram. We've got 1 pole from the denominator, 1 pole from the numerator, and you can see that the numerator gives us a 0 on the unit circle at z equal to -1. And the denominator gives us a pole at just about halfway out, a little less than halfway out. So there's our pole zero diagram, and then this plot over here was computed using freq z, using this transfer function. I know that because I see the superscript f there, which tells me that I am looking at a dTFT And so that's what we have. And just as a way of comparison, remember our cutoff frequency needed to be at pi over 4. Cutoff frequency, remember, means where it drops to 0.707. So that's the negative 3 dB point. And so I drew a horizontal line here at 0.707, and you can see that it intersects the response there. And if you draw a vertical line down, it goes to pi over 4. So we have now exactly achieved our design. So again, keep in mind that what we've done here is we've pre-warped our frequency out from, instead of we want 5 kilohertz to be the cutoff, we convert 5 kilohertz into radians. It's 31,000. If we were to put the 31,000 in here, we would end up with a cutoff frequency that's lower than where we want it to be. That's because of the warping. So we pre-warped it out. Instead of 31, we took it out to 33,000 and change. And now when it comes back in, it ends up at exactly pi over 4, and pi over 4 with a 40,000 samples per second sampling rate corresponds to 5,000 hertz. So we have our cutoff frequency exactly where we want it. So that's a nice little example there. And just to show how MATLAB allows you to do this very easily, you don't even have to do the pre-warping. It will do the pre-warping for you. It's built right into this bilinear transform command. So this first box shows us the original way that we did it. We did the pre-warping so that we got the 33,000, and we only needed to put 3 things in: numerator coefficients, denominator coefficients, and sampling rate. Then we ran bilinear, and we got our discrete time coefficients. If we use bilinear with the pre-warping feature, we get to tell the bilinear command, this is the frequency that we don't want warped. So that one frequency from the continuous time better end up exactly at the corresponding discrete time frequency for that frequency. So notice what we do. Instead of putting in 33, we put in our regular 31 in here. That's the equivalent of 5 kilohertz converted into radians per second. Then we put in our sampling rate, and then it asks for FP, and it says specified in hertz. So we are the frequency that we want to be pre-warped, so it ends up being exactly where it is our cutoff frequency. That's in radians per second, so we divide by 2 pi to get it into hertz. So now if we run the bilinear with the original 5 kilohertz cutoff frequencies put in with the pre-warping parameter properly inserted, run it, we get the same exact values out of this. So this shows how extremely useful and easy to use this idea of bilinear transform works. So the key is to understand how the warping and the pre-warping interact, and understand how you can either do it by hand or, if you prefer, do it with MATLAB. And I believe that is the end, and it is. And we'll say goodbye there, and I'll see you in the next set of notes.